Hello, I'm Laura Gonzalez, and I'm going to present you the progress of my PhD project, which take a look of the environmental driver of human salmonellosis. You might well ask yourself, salmonella again? But despite of being tired of hearing about salmonella and knowing so many things as we do about salmonella, it's a very well-known agent of foodborne disease. It is actually the second most common cause of foodborne disease in Europe and one of the leading causes of foodborne zoonosis in the world. Here you can see the CDC of the US publishes every year all the known outbreaks that have been related to salmonella, amongst other foodborne agents. But salmonella is always a loyal cause of disease, and it is linked to the most diverse types of foods like mushrooms, peaches, onions. Usually it's linked to fresh fruits, also meat, eggs. So it is, despite of being an old, well-known agent, it is still trendy in the foodborne world. The European CDC, the ECDC, has also similar epidemiological updates in its website. And again, salmonella is often present, and it even publishes yearly reports dedicated just to salmonellosis and analyzing year after year how is the incidence trend evolving in Europe and the type of food involved in these outbreaks. And it is known that there is a seasonal pattern in the cases of salmonellosis. For instance, if we plot the daily cases recorded, for example, in England and Wales, year after year we see this trend with the highest number of cases concentrated during the warmest months of the year, mostly August, September, and sometimes October. To make more evident this pattern, when we condense all the years in one single graph, like the one on the left, we can clearly see this peak of cases around the week 31st of the year. So in my project, we've seen this incident, but we want to understand why this happens. Why is this seasonal pattern happen, and how is the environment involved in this seasonality? So we will try to explain the environmental side of the salmonella incidents by using a multifactorial approach. This is by analyzing factor by factor everything that can be included in the environmental analysis, such as weather effects, demographics, land use, and animal distribution, everything that we can and is somehow related to the environment and its effects on the incidence of salmonellosis, we will try to analyze. We will do this by analyzing the existing evidence in the literature, since food is one of the main drivers of disease in human salmonellosis. We have found a mathematical link of the bacterial growth in eggs and chicken in relation with temperature. So we, by by involving the bacterial growth in a Gompertz curve, we can kind of predict the number of the bacterial growth in these kind of food products, depending on different temperatures. This from one side. From another side, since Salmonella is a relatively well-known agent of disease, we count with a very big data set of human salmonellosis in England and Wales, kindly provided by Public Health England. And we have these daily records with its geographical location for the years since the year 1987 to the year 2020. This, together with high-resolution climate data set provided by the Met Office, also with its geographical location for the years 1989 to 2020, and with the demographics through the years in the country. So all this together, we have embedded it to estimate the probability of detecting Salmonella in these products by modeling as a Poisson process. So we will get the probability of infection by multiplying the number of people living in an area times the probability of these people getting in contact with one food product. In this case we have analyzed egg and chicken, so probability of getting in contact with one egg and times the probability of this egg being contaminated with Salmonella. And summing both products, we will end in the estimation of the probability of a person getting infected due to an infected food product. For this, we have to make a series of assumptions, of course, and we will assume that one person will eat one egg, and that the more eggs the person eats, the more chances of getting infected. As a result, we will try to predict the probabilities of finding human cases for the given temperatures recorded for these years in the past. So, as a preliminary result, even if it will seem obvious, it is not as obvious as it may seem, the fact that we find more cases due to higher temperatures. So here we have modeled we have made a simulation of the probability of getting infected just by taking into account eggs and chicken alone and the growth of Salmonella in these products with temperature. So only temperature as an environmental variable and eggs and chicken as food sources of infection. In this graphic, you can see in red the recorded cases by Public Health England, and in green we see the simulation of the infection in humans due to chicken alone, and in blue due to eggs. So even if this graphic is quite small, I have aggregated all the years together in order to make it easier to understand the graph. But we can see that even if the curves don't match exactly the number of cases recorded by Public Health England, it does follow this type of seasonality. So just by predicting cases due to these products with temperature, we see an accumulation of cases at the same time as it happened, according to the records. So it's quite revealing that we can reproduce somehow the seasonality just with chicken and eggs and temperature. Of course, these graphs, these curves, don't fit exactly the real cases recorded, but by making more adjustments, by including more weather variables such as humidity and vapor pressure, and also if we find more food sources of contamination, and the estimation of the intake of each product in order to make a combined contamination from food alone, we will try to approximate our simulation to the real cases to make our model more precise, more realistic. And this in views to be, and as long as the moment we are able to reproduce the real cases for records that we know from the past, the better we will be able to make projections of the future based on weather assumptions. For example, if we are expecting the average climate temperatures to rise in the future years due to climate change, with our model well fit, we will be able to kind of estimate the expected number of cases due to this rise in temperatures. So even if this is a preliminary status, we are safe to say that temperature annex seems to have a big effect on the incidence of salmonellosis. But there are also other factors that need to be included. By including more food sources and more weather variables, we will continue to improve our model and ultimately wanting to understand better how salmonellosis is conditional on environment, and using this for useful practical public health applications, such as predicting the risk of disease under different climate scenarios by incorporating, as I just mentioned, climate change projections. In my future steps, I have also in mind performing a spatial analysis to look for just the relevant incidence difference between different regions, how the geographic influences the number of cases, if any, and also create a conditional incidence. That is, we have seen for the moment how temperature influences the cases alone, but if we incorporate another weather variable such as humidity, we want to see how they both interact to make a final effect, not just the effect of one variable alone, but the effect of the both variable combined. So that's what we will intend with the conditional incidence. If we have data enough to perform good quality analysis, we will try to include as well the effect that the abundance of livestock in the area, how this presence of animals influence, if any, the number of human cases. And also if we are able to include the health status or disease status of chicken and pigs in the incidents, we will also do. And once the model is more or less ready, we want to make the final validation by using data from another country in our model and see if our model is able to predict the cases as it does in England and Wales in other countries, and thus making stronger the model to be used in a wider scenario. So that is all from my side. Thank you very much for your attention, and I would love to have feedbacks, questions or comments. Feel free to ask me through my email, which is in the first slide, or to look me on LinkedIn. I'll be happy to connect. Thank you.